The universe is a masterpiece of unsolved mysteries. Our most powerful telescopes scan the depths, and sophisticated probes sail the void. Yet the cosmos remains filled with phenomena that defy all explanation. You are about to embark on a journey through 30 of the most perplexing cosmic enigmas. By the end, you will possess a front-row seat to the greatest unanswered questions at the very edge of human knowledge. We will confront an invisible substance holding galaxies together and a force tearing space itself apart. What could cause a star's light to vanish in impossible patterns, and what sent a single, shocking message from the void? Which cosmic mystery makes you question everything you thought you knew? The first great enigma is something we cannot see, touch, or measure directly, yet it is everywhere. Our story begins not in deep space, but with a simple, fundamental question. Why do galaxies stay together? Picture a cosmic carousel, a vast spiral of stars spinning at incredible speeds. According to the laws of gravity we understand, the outer stars should be flung into the void, scattering the galaxy across the cosmos. But they are not. Something is holding them in place, something that provides an immense amount of extra gravitational pull. That something is dark matter. It is the invisible scaffolding of the universe, a cosmic glue that binds galaxies and shapes the largest structures we see. We know it is there because of its gravitational signature. When astronomers map how fast stars orbit the center of their galaxies, the math only works if there is 5 times more material than all the visible stars, gas and dust combined. We see its handiwork through a phenomenon called gravitational lensing, where the gravity of a massive object, like a cluster of galaxies, bends the light from more distant objects behind it, acting like a cosmic magnifying glass. The amount of bending we observe often requires far more mass than we can see, revealing the hidden presence of dark matter. Even the faint afterglow of the Big Bang, the cosmic microwave background, bears its imprint, telling us that dark matter makes up roughly 27% of everything in the cosmos. Ordinary matter, the stuff of planets and people, accounts for less than 5%. So the overwhelming majority of the universe's material is this mysterious, unknown substance. We have been searching for it for decades with detectors buried deep underground in particle colliders and with telescopes scanning the skies. We have ruled out many possibilities, but the fundamental question remains unanswered. What is dark matter made of? Is it a sea of exotic, undiscovered particles that barely interact with light? Or could it be something even stranger, a flaw in our understanding of gravity itself? This is the shadow that shapes the cosmos, the first and most profound mystery on our list. But if dark matter is the mysterious glue holding the cosmic structure together, then its counterpart is an even more baffling anti-glue, a force working in direct opposition. This brings us to our second cosmic mystery, dark energy. For most of the 20th century, astronomers believed the expansion of the universe, set in motion by the Big Bang, was gradually slowing down. Gravity, the attractive force of all that matter, was thought to be pulling back on the cosmic reins. Then, in 1998, 2 independent teams made a discovery so shocking it would win them the Nobel Prize. They were measuring distant supernovae, the explosive deaths of white dwarf stars which serve as cosmic mile markers. By observing how much their light had stretched or redshifted, scientists could calculate how fast the universe was expanding at different points in its history. The data revealed something impossible. The expansion was not slowing down, it was speeding up. Something was pushing galaxies apart with ever-increasing force, overpowering the collective gravity of all the stars, planets, and even dark matter. That something is dark energy. It is not a substance you can point to, but rather a property of empty space itself. Think of the vacuum of space not as nothing, but as a seething sea of potential energy. As the universe expands, more space comes into existence, and with it, more of this repulsive energy. This creates a feedback loop of acceleration, a runaway cosmic engine we do not understand. The numbers are staggering. Dark energy is estimated to make up about 68% of the entire cosmos. Combined with dark matter, this means that over 95% of the universe is composed of forces and materials completely unknown to us. The leading explanation for dark energy is a revival of an old idea from Albert Einstein called the cosmological constant. He originally introduced it as a mathematical fudge factor to keep the universe static, later calling it his greatest blunder. Now it seems it might describe the energy of the vacuum itself, but the calculated value from quantum physics and the observed value from astronomy are off by a factor of 1 followed by 120 zeros, the worst mismatch in the history of science. This tells us our theories are profoundly incomplete. The ultimate fate of the cosmos hinges on the nature of dark energy. If it continues to accelerate expansion as it does now, distant galaxies will eventually vanish over the cosmic horizon, their light never again reaching us. In a more extreme scenario called the Big Rip, dark energy could grow stronger over time, overwhelming not just the space between galaxies, but the very forces holding atoms together, tearing all matter apart in a final catastrophic moment. From a mysterious pull to an inexplicable push, we are left with a universe where the dominant forces are shadows and pressure from the void. While dark energy pushes the entire cosmos apart on the grandest scales, a contradictory and deeply local force is pulling us in. Our Milky Way galaxy is not simply drifting aimlessly through the expanding universe. It is racing along with our entire local galactic group toward a specific, mysterious point in the sky at a staggering 2,200,000 kilometers per hour. This is the pull of the Great Attractor. Imagine the most powerful gravitational well you can conceive, a place where space-time itself seems to funnel inward, drawing everything toward it like water toward a cosmic drain. This anomaly lies approximately 250 million light-years away in the direction of the constellation Centaurus, but there is a profound problem. The very center of this gravitational pull lies directly behind the plane of our own galaxy, in a region astronomers call the zone of avoidance. This is the thick, dusty, star-choked disk of the Milky Way, which acts like a dense cosmic fog, blocking our view of the universe beyond invisible light. For decades, the Great Attractor was a ghost, a statistical tug felt in the motion of thousands of galaxies but impossible to see. What could possibly possess enough mass to pull millions of galaxies, including our own, off course? The quest to see behind the veil required new eyes. Astronomers turned to telescopes that could see through the dust using X-ray and infrared light. These observations began to peel back the galactic curtain, revealing not a single monstrous object, but something perhaps even more significant. The Great Attractor appears to be the heart of a colossal supercluster of galaxies, a gravitational nexus where many immense filaments of the cosmic web converge. We now know it is part of an even larger structure called the Laniakea supercluster, a vast continent of galaxies spanning over 500 million light-years, of which our Milky Way is merely a distant suburb. Yet the mystery deepens. The mass of all the visible galaxies in this region still does not fully account for the immense pull we feel. This suggests that the true engine of the Great Attractor is likely an unfathomable concentration of dark matter, the universe's invisible scaffolding, pooled in a density that defies imagination. So we are caught in a cosmic tug-of-war between the outward push of dark energy and the inward pull of a hidden gravitational giant. Our journey toward it is a voyage into the darkest blind spot of our own sky, a reminder that the greatest mysteries are sometimes hidden in plain sight, just behind the glittering veil of our own galactic home. From the immense, slow pull of the Great Attractor, we now turn to a cosmic phenomenon that is its exact opposite in every way, a signal so brief and violent it defies all expectation. Deep space occasionally erupts with a flash of radio waves of almost unimaginable power, a burst so short it would be over in the blink of an eye, yet so energetic it can outshine entire galaxies. These are fast radio bursts, detected as a single, sharp spike on a radio telescope's data plot. An FRB releases more energy in 1 millisecond than our Sun does over 80 years. The first one was discovered in 2007, buried in archival data from a radio telescope in Australia, and for years they were considered rare and possibly terrestrial glitches. But then we found more, and the mystery exploded. The key question became, what kind of cosmic powerhouse could possibly create such a brief, brilliant flash? The initial theories pointed to cataclysmic, one-time events, the final, fatal screams of celestial objects. Imagine a neutron star, the ultra-dense corpse of a massive star, collapsing into a black hole. Or two neutron stars in a deadly dance, spiraling inward and merging in a titanic collision. Such events could, in theory, produce a single, tremendous blast of radio waves. But the cosmos had a surprise in store. In 2016, astronomers made a landmark discovery, a fast radio burst that repeated. It flashed once, went silent, and then flashed again from the exact same point in the sky. This changed everything. A repeating FRB cannot be the product of a one-time destruction, like a stellar explosion or merger. Its source must survive the blast, meaning it is powered by an object that can fire off these incredible salvos again and again. The prime suspect now is a type of neutron star with the most powerful magnetic field in the universe, a magnetar. Picture a city-sized object with a magnetic field so strong it could strip the information from every credit card on Earth from halfway across the solar system. A starquake on the surface of such a monstrous object, a sudden cracking of its rigid crust, could theoretically unleash a torrent of energy that we see as a fast radio burst. Some repeating bursts even show a strange pattern, a chaotic period of activity followed by a long silence, like a cosmic volcano with an unpredictable eruption schedule. Yet, even the magnetar theory faces challenges. The sheer energy of the most powerful bursts pushes the limits of what we think these objects are capable of. This has led to more exotic, speculative ideas. Could they be the power beams of advanced alien civilizations, a concept scientists take seriously enough to study and rule out natural explanations first? Or are they signatures of cosmic strings, hypothetical defects in the fabric of space-time, or the energetic wakes of asteroids falling onto pulsars? Each new detection adds a twist. We have now traced some bursts back to their home galaxies, finding they come from all types of environments, from turbulent star-forming regions to quiet, older galaxies. This diversity suggests there might not be one single answer, but multiple cosmic engines capable of generating these fleeting, universe-spanning screams. They are the ultimate cosmic transients, brief messages in a bottle washed ashore from oceans of space and time, carrying with them the encrypted signature of physics under conditions we can scarcely dream of recreating. That fleeting, brilliant scream of a fast radio burst echoes a much older, and in some ways more haunting, mystery from our own cosmic backyard. On a quiet Ohio night in August 1977, the Big Ear radio telescope at Ohio State University was engaged in its routine, patient sweep of the heavens, listening for whispers in the static. It was part of the search for extraterrestrial intelligence, or SETI, a long-shot project scanning for any pattern in the cosmic noise that might suggest a mind behind it. For the most part, the data printouts were a monotonous stream of numbers and letters, representing the faint hiss of natural cosmic radio sources. Then, on August 15th, the system recorded something utterly different. For 72 seconds, a signal blasted through the receiver, growing in intensity and then fading away, perfectly matching the expected signature of a fixed, distant source passing through the telescope's stationary beam. It was so powerful that it maxed out the equipment scale. When volunteer astronomer Jerry Amon reviewed the data printout the next day, he was stunned. Circling the alphanumeric sequence representing the signal's strength, he simply wrote in red ink, "Wow." The exclamation point said it all. This was the signal SETI researchers had dreamed of finding. It came from the direction of the constellation Sagittarius, near a star group called Chi Sagittarii, and it was concentrated on one specific frequency, 1420 MHz. This detail is crucial because that frequency sits in a protected radio band, a quiet channel where earthly transmissions are forbidden. It is a band where hydrogen, the most common element in the universe, naturally emits a faint whisper. The logic was that an advanced civilization might use this universal landmark as a natural hailing frequency, a cosmic water cooler where everyone might listen. The WOW signal fit the profile perfectly. It was narrow band, meaning it was not the broad spectrum crackle of a natural astrophysical event. It was incredibly strong. And it came from a fixed point in deep space. The search for a repeat began immediately and has never stopped. Astronomers have pointed the most powerful radio dishes on Earth back toward that spot hundreds of times over the decades. The silence has been absolute. Nothing like it has ever been heard again. This one-sided conversation is the heart of the mystery. If it was a message, we heard only one word. Natural explanations have been proposed, but each has a serious flaw. Could it have been a reflection of a human satellite signal bouncing off space debris? The frequency was protected, making a terrestrial source very unlikely, and no known satellite matched the profile. More recently, some suggested it was caused by hydrogen clouds surrounding a passing comet, but the comets proposed were not in that region of the sky at that time. The signal's singular nature is its most baffling characteristic. Most cosmic phenomena, from pulsars to solar flares, repeat. They are part of the universe's regular machinery. The WOW signal was a one-time event, a perfect 72-second tone that appeared, declared its presence with shocking clarity, and vanished forever into the static. That original computer printout with its circled alphanumeric code and that singular handwritten WOW has become an icon of our cosmic loneliness. It stands as a testament to a moment when the universe seemed to speak directly to us, only to leave us with a question that has echoed for nearly 50 years. Was it a cosmic coincidence, a freak natural event we still do not understand, or was it a fragment of a message, a postcard from the void that arrived once and was never sent again? In a cosmos filled with repeating bursts and constant gravitational tugs, the profound silence that followed a single, perfect note may be the most unsettling mystery of all. The profound silence following the WOW signal left us listening for a pattern that never repeated, but sometimes the universe communicates not through radio whispers but through a star that simply blinks. In the constellation Cygnus, about 1,470 light-years away, a star designated KIC 8462852, now famously known as Tabby's star, behaves in a way that defies every textbook. Discovered not by a lone astronomer in a control room, but by a global army of citizen scientists sifting through public data from NASA's Kepler Space Telescope, this star's story began with a pattern of light that made no sense. Kepler's mission was to find exoplanets by detecting the tiny, regular dips in a star's brightness caused by a planet passing in front of it. Tabby's star did dip, but its behavior was anything but regular. Its light would sometimes fade by a minuscule amount consistent with a planet, but then, without warning, it would plunge into dramatic, irregular dimming events, losing up to 22% of its light for days or weeks at a time. The pattern was chaotic, asymmetric, and utterly unprecedented. A planet, even a giant one, blocks at most about 1% of a star's light and does so with clockwork regularity. This was something else entirely. Something was passing in front of this star in vast, ragged swarms with no discernible rhythm. The leading early hypothesis proposed by the star's namesake astronomer Tabitha Boyajian was a colossal cloud of comets. Picture a family of comets so vast, perhaps the fragmented remains of a shattered icy planet, orbiting the star in a tight, chaotic cluster. Their dusty tails could, in theory, block starlight in irregular chunks. But the scale required was staggering, involving hundreds of thousands of giant comets, a scenario that seemed almost as unlikely as the more sensational idea it provoked. That idea, of course, was alien megastructures. The physicist Freeman Dyson once speculated that a sufficiently advanced civilization would eventually need to capture most of its star's energy, perhaps by constructing a vast swarm of orbiting collectors, a so-called Dyson sphere. Such a structure, incomplete and under construction, would block starlight in exactly the bizarre, irregular patterns observed at Tabby's star. The internet and even parts of the scientific community ignited with the possibility. Here, at last, might be tangible evidence of intelligence operating on a stellar scale. The star became a global sensation, a focal point for our deepest hopes and wildest speculations. Science, however, demands evidence. Follow-up observations across the electromagnetic spectrum have since painted a more complicated, but no less mysterious picture. Detailed studies show the dimming is more pronounced in blue light than in red light. This is a crucial clue. It means whatever is blocking the light is not solid and opaque, like a planet or a solid megastructure. It is translucent and made of fine particles like dust or smoke. This finding severely challenges the alien megastructure hypothesis and also makes the giant comet swarm idea problematic, as comet dust should be quickly blown away by stellar radiation. Other observations revealed the star has also been very slowly but steadily dimming over the past century, a long-term fade that adds another layer of intrigue. So what is happening? The current best guesses are still cosmic in their weirdness. Perhaps the star is surrounded by a vast, warped ring of dust, like Saturn's rings on a monstrous scale, with clumps and arcs that transit erratically. Maybe the star recently devoured a planet, and we are seeing the chaotic aftermath of that destruction, a cloud of debris slowly settling into a new configuration. Or possibly, Tabby's star itself is undergoing some rare and poorly understood phase of stellar activity, belching out immense clouds of its own material. Every proposed solution feels like trying to fit a square peg into a cosmic round hole. The core mystery remains stubbornly intact. Tabby's star stands as a monument to the fact that even when we rule out the extraordinary, like alien engineering, the universe can still present us with a natural phenomenon so strange it stretches our imagination to the breaking point. It is a reminder that the cosmos has a flair for the dramatic, capable of staging a light show so inexplicable that, for a moment, the line between natural wonder and science fiction beautifully, tantalizingly blurs. The bizarre light of Tabby's star forces us to confront a deeper, more unsettling silence. With billions of stars in our galaxy alone, many hosting Earth-like worlds, the cosmos should be a vibrant, noisy arena of life. Yet all our telescopes here is a profound and endless quiet. This is the Fermi paradox, named for the physicist Enrico Fermi, who, over a casual lunch in 1950, posed a devastatingly simple question. Where is everybody? The logic is compelling. Our Milky Way galaxy contains hundreds of billions of stars. Conservative estimates suggest tens of billions of these could have rocky planets orbiting in the habitable zone where liquid water could exist. Life on Earth arose relatively quickly once conditions were stable, suggesting the step from chemistry to biology might be common. If even a tiny fraction of those worlds developed intelligent life, and if just a handful of those civilizations mastered interstellar travel over the galaxy's 13 billion-year history, the entire Milky Way should have been colonized many times over. We should see the signs everywhere, from vast engineering projects to the radio chatter of a million civilizations. Instead, we see nothing. The silence is deafening. This contradiction between high probability and zero evidence is the paradox at the heart of our cosmic loneliness. Scientists have proposed many possible solutions, each more thought-provoking than the last. One of the most sobering is the concept of the Great Filter. This idea suggests that somewhere between the emergence of life and the development of a galaxy-spanning civilization, there is an evolutionary or technological barrier so immense that almost no species ever passes it. The terrifying question is, where is this filter located? Is it behind us, meaning the step from non-life to life, or from simple cells to complex intelligence, is miraculously rare, and we have already beaten astronomical odds? Or more chillingly, is the Great Filter ahead of us? Perhaps every advanced civilization reaches a point, maybe through nuclear war, environmental collapse, or a dangerous technology we have not yet invented, that causes its own inevitable destruction. Our empty sky, in this view, is a cosmic graveyard. Other solutions are less grim but equally strange. The zoo hypothesis suggests we live in a kind of galactic wildlife preserve, that advanced civilizations are aware of us but have chosen a strict policy of non-interference, observing us from a distance until we reach a certain maturity. There is the possibility that we are simply too early or too late, that intelligent life is separated by vast gulfs of cosmic time, with civilizations blooming and dying like fireflies in the night, never overlapping. Or perhaps the truth is that we are looking for the wrong things. A civilization 1,000,000 years more advanced than ours might not use radio waves, a technology we have barely used for a century. Their communications or their artifacts might be so far beyond our comprehension that we are staring right at them without understanding what we see. They might have transformed into something unrecognizable, perhaps uploading their consciousness into virtual realities or merging with their technology, leaving the physical universe quiet. The famous Drake equation attempts to frame this problem mathematically, multiplying factors like the rate of star formation and the fraction of planets that develop life. But every term in that equation is a giant question mark. The Fermi paradox is not just an astronomy puzzle, it is a mirror. It forces us to consider the fragility and rarity of our own existence, and the immense responsibility that comes with being, for now, the only voice in the chorus we can hear. That silence from the stars is the most important message we have ever received, and we are only just beginning to understand what it might be trying to tell us. That profound silence from the cosmos is a reminder of just how difficult it is to measure anything with certainty across the vast emptiness. Sometimes the greatest mysteries are not found in distant galaxies, but in the subtle, unexpected behavior of our own robotic explorers. For decades, 2 spacecraft on a one-way journey to the stars presented scientists with a tiny, nagging puzzle that refused to go away. This is the Pioneer anomaly. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were true trailblazers. After completing their primary missions to Jupiter and Saturn, they continued on ballistic trajectories, coasting out of the solar system toward interstellar space. As they receded, scientists meticulously tracked their speed by measuring the Doppler shift in their radio signals, an exquisitely precise technique. Over time, a consistent and utterly unexpected signal emerged in the data. Both spacecraft were experiencing a tiny, unexplained deceleration, a constant, minuscule pullback toward the Sun. This force was incredibly small, about 10 billion times weaker than the gravity we feel on Earth's surface, but it was there and it was real. It was as if the ghosts of the solar system were reaching out with faint hands trying to tug the probes back. For years, this anomaly fueled intense speculation. Had we discovered a flaw in our understanding of gravity itself, a hint that Einstein's theory of general relativity needed modification at the largest scales? Was there some unknown, diffuse material in the outer solar system, a haze of dark matter or fine dust creating just enough drag to slow the Pioneers? Or was the answer something even more exotic? The mystery persisted for over 30 years, a testament to the challenge of accounting for every single influence on a spacecraft billions of miles from home. The eventual solution was a masterpiece of forensic engineering, a lesson in humility. A team of researchers launched a monumental effort to recover the original design documents, some stored only on microfilm and paper, and reconstruct a thermal model of the Pioneer spacecraft in incredible detail. They realized the answer was not in the void but in the spacecraft themselves. The Pioneers were powered by radioactive thermoelectric generators, which produced heat as a byproduct of generating electricity. That heat radiated away from the spacecraft unevenly. More importantly, the main dish antenna acted like a one-way mirror, reflecting thermal radiation from the back of the spacecraft forward toward the sun. This created a tiny but constant photon thrust, a gentle push from the spacecraft's own warmth acting in the exact opposite direction of its travel. It was not a pull from the sun, but a push from behind. When this thermal recoil force was finally and painstakingly calculated and applied to the trajectory models, the anomalous deceleration vanished. The Pioneer anomaly was solved. Yet, this solved mystery is perhaps more illuminating than an unsolved one. It underscores an incredible truth about deep space exploration. In the pristine quiet of the outer solar system, far from the gravitational tugs of planets, the tiniest of effects become measurable. The gentle pressure of sunlight, the minuscule outgassing from a spacecraft's paint, even the heat from its own electronics, can mimic the signatures of new physics. It is a cosmic game of precision, where separating a revolutionary discovery from a mundane engineering detail requires almost supernatural levels of accounting. The Pioneers taught us that to hear the true whispers of the universe, we must first learn to silence the faintest hum of our own machines. That meticulous accounting for every photon of heat from the Pioneer probes shows just how carefully we must listen to the cosmos. But what if, when we finally tune our instruments to the faintest whisper of all, the universe itself seems to be whispering our name? This brings us to a finding so statistically unsettling that astronomers half-jokingly named it the axis of evil. It is a mystery written in the oldest light there is, the cosmic microwave background. This faint, cold glow is the relic radiation from the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. For decades, it has been our most powerful tool for understanding the cosmos's birth, showing a beautiful, nearly uniform tapestry of tiny temperature fluctuations that seeded all future galaxies. Yet, when scientists created exquisitely detailed maps of this ancient light, they noticed something that should not be there. On the very largest scales, some of the patterns in this primordial soup appear strangely aligned with the plane of our own solar system. Imagine finding a fossil from the dawn of life on Earth, and etched into its surface is a faint but unmistakable outline of the continent you are standing on. According to the foundational principle of cosmology, the universe should have no preferred direction, no center, and no special place. The cosmos should look statistically the same in every direction, a concept called isotropy. The alignment with our insignificant little solar plane is therefore cosmically egotistical and theoretically impossible. It suggests that either we are, against all odds, sitting in a privileged location in the universe, or there is a fundamental flaw in our standard model of cosmology. The axis refers to a specific direction in space around which these large-scale anomalies seem to pivot. The evil part is a playful nod to how deeply this finding disturbs our comfortable assumptions. One of the most prominent anomalies is a mysterious cold spot, an area of the sky significantly colder than the average, and a strange alignment of the larger hot and cold blobs that seems to create a kind of cosmic asymmetry pointing right back at us. The immediate and most likely explanation is that we are being fooled. This could be a systematic error, some subtle contamination in the data from our own galaxy's foreground emissions that we have not perfectly subtracted. Or it could be a statistical fluke, a cosmic coincidence that, in a universe of infinite possibilities, just happens to look personal. but after multiple satellite missions from WMAP to Planck have all seen hints of these anomalies, the fluke argument is wearing thin. If it is real, the implications are staggering. It could mean the universe is not isotropic on the largest scales, that it has a fabric with a subtle grain or direction to it, like cosmic wallpaper with a pattern we can only see from a certain angle. Some theorists have proposed truly mind-bending ideas to explain it. Could our universe have collided with another bubble universe in the multiverse during its earliest moments, leaving a bruise on the cosmic microwave background? Or does it point to a pre-Big Bang structure, a remnant of something that existed before our cosmos began? The axis of evil forces a profound and humbling question. Are we reading the universe's first chapter correctly, or have we, from our tiny vantage point, mistakenly interpreted a smudge on the lens as a feature of the distant horizon? This alignment, whether a ghost in the data or a crack in our theories, reminds us that the universe's oldest story might still have secrets we are not yet equipped to understand. If the oldest light in the universe seems to whisper our name, then the most violent particles scream it. From the depths of space, a relentless rain falls upon our planet, not of water, but of atomic shrapnel moving at nearly the speed of light. These are cosmic rays. They are not rays at all, but mostly protons, the nuclei of hydrogen atoms that have been flung across the galaxy by forces of unimaginable power. They constantly pepper our atmosphere, creating beautiful secondary showers of light we see as auroras, and posing a radiation hazard for astronauts. For the most part, their energies are impressive but understandable, likely boosted by the shockwaves of exploding stars. But on one October night in 1991, something impossible happened. The Fly's Eye cosmic ray detector in Utah recorded a single subatomic particle, a proton, hitting our atmosphere with a force that defied all reason. Its energy was calculated to be about 50 joules. That might not sound like much until you realize this energy was packed into a single, tiny proton, a particle so small it is essentially a mathematical point. To give that scale, this one proton carried the kinetic energy of a baseball pitched at 90 miles per hour. It was moving at such a ludicrous fraction of light speed that, in its own frame of reference, it could have crossed our entire galaxy in just minutes. The physicists who discovered it could only utter one phrase, the "oh my God" particle. This was not just a record breaker, it was an anomaly that shattered the theoretical ceiling. According to our best models, a proton with that much energy should not be able to travel very far through the cosmos at all. It should smash into the faint glow of the cosmic microwave background, the leftover radiation from the Big Bang, and lose its energy in a catastrophic collision long before it ever reached Earth. Its very existence here tells us something is fundamentally wrong with our understanding. Either our models of particle physics are incomplete, or this proton did not come from very far away, which presents its own profound puzzle. What kind of cosmic accelerator, right in our galactic neighborhood, could possibly do this? Imagine a natural particle collider so powerful it makes the Large Hadron Collider here on Earth look like a child's toy. The usual suspects fall short. Even the most violent supernova shockwaves seem incapable of reaching these energies. The jets from active supermassive black holes, quasars blasting matter across millions of light years, are strong candidates, but the nearest ones are far away, and the particle should have been slowed by its long journey. Could it have come from the collapse of a cosmic string, a hypothetical defect in space-time itself, or from the annihilation of dark matter particles in a dense cluster? Every explanation feels like a desperate reach for a power source we have never witnessed. The mystery only deepens. Since that first detection, a handful of other ultra-high energy cosmic rays have been recorded, each one a singular event pointing back to a random spot in the sky with no obvious source. They are cosmic snipers firing a single, unimaginably powerful bullet from the void. We have built vast observatories like the Pierre Auger Observatory in Argentina, covering an area the size of Rhode Island with detectors to catch these rare events and trace their paths backward. Yet the sky remains silent of any obvious culprit. The origin of the oh my god particle and its kin is more than a physics puzzle, it is a direct challenge. It tells us that somewhere, perhaps hidden in plain sight, the universe operates a natural accelerator of such ferocious power that it can hurl a single, fundamental piece of matter with the force of a major league pitch. Finding that engine would not just solve a mystery, it would open a window into the most extreme and violent processes at work in the cosmos today. That single, impossibly energetic proton was a bullet fired from a cosmic gun we cannot find. But sometimes the mystery is not a presence but a profound absence, a place where the expected cosmic clutter simply vanishes. Far beyond the orbit of Neptune, in the cold, dark frontier of our solar system, lies a region of frozen leftovers called the Kuiper Belt. This is the home of Pluto and thousands of other icy worlds, the raw building blocks of planets that never formed. For years, astronomers expected this belt of debris to extend smoothly outward, gradually thinning as it merged with the even more distant Oort cloud. But the data from powerful telescopes revealed something startling. There is a cliff, at about 50 astronomical units from the Sun, roughly the orbit of Pluto. The population of Kuiper Belt objects is robust. But just a little farther out, beyond this invisible line, the number of detectable icy bodies plummets by a factor of nearly 100. It is as if someone drew a boundary in the solar system and swept everything beyond it away. This is the Kuiper Belt Cliff. The solar system's disk of primordial material does not fade gently into the void. It ends abruptly and inexplicably. This sharp edge defies our basic models of how planetary systems form from swirling disks of gas and dust. That disk should have extended much farther, and its icy remnants should still be there, orbiting in the deep freeze. So what happened to them? One compelling theory points the finger inward, toward a gravitational giant we have yet to see. The hypothetical planet 9, a world perhaps 10 times the mass of Earth orbiting hundreds of times farther out than our own planet, could be the architect of this cliff. Its immense gravity, over billions of years, could have shepherded the distant Kuiper Belt objects into strange, tilted orbits, clearing out a vast zone in the process. The cliff's location would then be a signature of this hidden planet's influence, a gravitational fence post marking its domain. But there is another, more dramatic possibility that looks outward to a stellar intruder. In the Sun's fiery infancy, our star was born in a crowded stellar nursery alongside thousands of others. What if a sibling star passed perilously close to our young solar system? Such a close encounter would have been a gravitational catastrophe, violently stripping away the outer reaches of the protoplanetary disk before it could coalesce into more objects. The Kuiper Belt Cliff would be the fossilized scar of that stellar flyby, a permanent reminder of a chaotic birth, or perhaps the answer is a quieter process. Some models suggest that the early Kuiper Belt was once much more massive and extended, but over eons, the gentle but persistent drag of interstellar gas slowly eroded the orbits of the most distant objects, causing them to drift away or fall inward. Each theory paints a different picture of our solar system's history, one of hidden planets, stellar bullies, or the slow friction of the galactic environment. This empty zone at the edge of our home is a silent puzzle. It tells us that even the architecture of our own celestial neighborhood holds secrets, and that the story of how our solar system found its final shape is still being written in the dark beyond the last known world. The empty frontier of our Kuiper Belt is a puzzle of absence, but on a world we can clearly see, a storm rages with impossible geometry. At Saturn's North Pole, a structure so perfect it looks engineered spins in the planet's thick atmosphere. This is the Saturn hexagon, a six-sided jet stream roughly 25,000 kilometers across, large enough to swallow 4 Earths side by side. Discovered by the Voyager probes in the 1980s and observed in stunning detail by the Cassini spacecraft decades later, this is not a fleeting cloud formation. It is a permanent, towering feature, a hurricane with 6 razor-sharp sides that has endured for at least 4 decades, and likely much longer. The hexagon is a standing wave pattern, a kind of atmospheric oscillation, but the scale and precision are utterly baffling. Think of it as a cosmic version of the vibrations that create patterns on a vibrating plate of sand. When the plate vibrates at certain frequencies, the sand arranges itself into geometric shapes like squares or hexagons. Something similar is happening in Saturn's atmosphere, where different layers of gas are moving at different speeds, creating a shear that can stabilize a wave into a fixed polygon. Laboratory experiments with spinning fluids have successfully created similar polygons, including hexagons, proving the basic physics is possible. But translating a tabletop experiment to a planetary scale introduces staggering complexities. The forces that create and sustain a perfect hexagon the size of a planet, with sides that appear nearly straight and vertices that are sharply defined for generation after generation, are not fully understood. It is a fluid dynamics puzzle writ large across an alien sky. Cassini's breathtaking infrared and visible light images revealed the hexagon's structure in mesmerizing detail, showing it as a deep-rooted jet stream with winds screaming at over 320 kilometers per hour. Inside its walls, smaller vortices spin and dance like subsidiary storms trapped in a colossal geometric cell. The stability is thought to be linked to Saturn's rapid rotation and the specific conditions in its polar atmosphere, but the exact recipe remains elusive. Why a hexagon and not a pentagon or an octagon? The shape likely depends on the speed differential between atmospheric bands and the planet's own rotation rate, a delicate balance that on Saturn defaults to 6. Yet, maintaining that balance against the chaotic turbulence of a giant planet's weather system is a feat of natural engineering we are still striving to comprehend. The hexagon stands as a majestic reminder that even within our own solar system, on a world we have visited with our robotic proxies, the atmosphere can sculpt forms of such mathematical purity that they seem to belong more to the realm of abstract art than to planetary science. It is a storm with perfect angles, a whirlwind trapped in a shape, whispering secrets about the fluid hearts of gas giants that we are only beginning to decode. While Saturn's atmosphere dances with geometric perfection, the thin, cold air of Mars holds a chemical whisper that has sent shockwaves through the scientific community. The story of Martian methane is a detective tale written in parts per billion, a trace gas that appears and vanishes in a pattern no one can yet explain. Our rovers, from the plucky Curiosity to the advanced Perseverance, have repeatedly sniffed out sudden, fleeting spikes of methane in the Martian atmosphere. On our own planet, methane is a potent biological signature. Over 90% of Earth's atmospheric methane is produced by living organisms, from microbes in wetlands to the digestive systems of livestock. So when our robotic proxies on another world detect it, the immediate, thrilling question is unavoidable. Are we smelling the faint, gaseous breath of Martian microbes? The possibility is intoxicating. Imagine simple, resilient life forms, perhaps dwelling in briny aquifers deep beneath the frozen Martian soil, metabolizing rocks and water to produce this gas as a byproduct. It is a scenario that fits within the harsh realities of the red planet, but biology is not the only chef that can cook methane. A purely geological process called serpentinization can also produce it. When certain minerals, like olivine, come into contact with water in a chemical reaction, they can generate methane as a byproduct. Mars has the right rocks and strong evidence of a watery past, making this a compelling non-biological explanation. The mystery is deepened not by the presence of the gas, but by its bizarre behavior. The methane does not linger and mix evenly into the atmosphere as scientists would expect. Instead, it appears in dramatic, localized puffs that vanish within a matter of weeks, far faster than known chemical processes can account for. It is as if Mars is briefly exhaling, then holding its breath. The European Space Agency's Trace Gas Orbiter, a spacecraft specifically designed to sniff the Martian atmosphere with incredible sensitivity, has paradoxically reported finding no methane at all from high altitude, even while Curiosity was measuring a spike just below on the surface. This suggests the gas is not only sporadic but also confined to the immediate ground level, pointing to a source that releases it and a destructive mechanism that acts with startling speed. What could be destroying the methane so quickly? Unknown atmospheric chemistry, perhaps involving electrostatic forces or exotic minerals on the surface, is a leading candidate. Or perhaps the methane is being rapidly absorbed into the porous regolith. Each new data point adds a twist. The spikes often coincide with the warmer Martian summer months, hinting at a seasonal process like subsurface ice melting and releasing trapped gas or stimulating microbial activity. The graph of these detections is not a steady line, but a series of silent stretches punctuated by sharp, enigmatic peaks. Solving this puzzle requires determining if the source is a biological whisper or a geological sigh. The upcoming Mars Sample Return mission, which aims to bring carefully selected rock and soil cores back to Earth, may finally provide the definitive answer. Until then, the intermittent scent of methane on the red planet remains one of the most tantalizing clues in the greatest detective story of all, the search for life beyond Earth. It is a faint signature in a rusty sky, a promise that the most profound discovery in human history might be hiding just beneath our robotic rover's wheels. That faint chemical whisper on Mars is a mystery confined to a single world, but in 2017, the solar system received a visitor from a realm entirely beyond it. A telescope in Hawaii, part of the Pan-STARRS survey scanning for near-Earth asteroids, spotted a faint point of light moving at impossible speed. Designated 1I 2017 U1, it was soon given a name from the Hawaiian language Aumuamua, meaning scout or messenger from the distant past. This was not a resident of our solar system. Its hyperbolic trajectory and blistering velocity of 92,000 kilometers per hour confirmed it was the first object ever detected that had arrived from interstellar space, a cosmic wanderer passing through our neighborhood. As telescopes around the world swiveled to observe it, the data that came back was stranger than anyone could have predicted. First was its shape. Based on how its brightness changed dramatically as it tumbled end over end, astronomers deduced it was highly elongated, perhaps 10 times longer than it was wide. Imagine a cosmic cigar or a flattened pancake tumbling chaotically through the void. No asteroid or comet in our solar system has such an extreme proportions. Second, as it swung around the sun and began its exit, it did something even more perplexing. It accelerated slightly, as if given an extra push. Comets do this all the time as sunlight vaporizes their icy surfaces, creating a jet of gas that acts like a natural rocket engine. But Oumuamua showed no visible coma, no fuzzy envelope of gas and dust that is the hallmark of a comet. It appeared as a sterile, rocky point of light, yet something was nudging it off a purely gravitational path. This non-gravitational acceleration launched a firestorm of debate. The leading natural explanation proposed that Oumuamua was in fact a comet after all, but an exotic one. Perhaps it was a fragment of a nitrogen ice world similar to Pluto that had been chipped off its home planet eons ago. As it approached our sun, the intense heat could have caused the solid nitrogen to sublimate, providing the thrust without producing the dusty coma we expect from water ice comets. Another idea suggested it was a very porous, fluffy aggregate of dust, a cosmic dust bunny whose low density allowed radiation pressure from the sun itself to give it the observed push. Yet each natural model felt like a stretch, requiring a type of object we had never seen before. The strangeness of its properties, however, opened the door to a more sensational speculation. Could Oumuamua be an artifact of an alien civilization? The prominent astronomer Avi Loeb famously proposed it might be a light sail, a thin, manufactured object pushed by starlight, perhaps a discarded piece of technology or a defunct probe. Its unusual shape and acceleration, while not proof, were consistent with such a concept. The scientific community largely pushed back, arguing extraordinary claims require extraordinary evidence and that unusual natural phenomena should be exhausted first. But Oumuamua was already racing away, too faint and too fast for further detailed study. By the time we realized how bizarre it was already a fading speck in the depths beyond Neptune. We had a few weeks of frantic observation, and then it was gone forever, back into the interstellar dark from whence it came. Artist concepts depict it as a dark red, elongated slab tumbling silently past the sun, a fleeting silhouette against the stars. Its brief passage left behind more questions than answers. Was it a nitrogen iceberg from a distant Pluto-like world, a shattered remnant from another star's planetary formation, or something even more unimaginable? Oumuamua remains a single, enigmatic data point, a messenger that delivered its cryptic note and vanished, reminding us that the galaxy is likely filled with such unseen travelers, each one a potential key to understanding the diversity of worlds we have yet to dream of. Oumuamua's silent passage was a mystery of form and motion, but the ultimate cosmic sinkhole presents a paradox that threatens the very foundations of physics. When anything crosses the boundary of a black hole, the event horizon, it vanishes from our universe. According to Albert Einstein's theory of general relativity, that is the end of the story. The object is crushed into the singularity, its mass, charge, and spin added to the black hole's ledger, but every other detail about it, the information that made it a book or a star or a person, is lost forever. The universe, in this view, has a permanent shredder, yet quantum mechanics, the rules governing the subatomic world, states with absolute certainty that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is the black hole information paradox, a direct clash between our two most successful theories of reality. For decades, physicists believed the information was simply trapped inside, locked away beyond the reach of science. Then Stephen Hawking made a discovery that turned the paradox into a crisis. He showed that black holes are not completely black. Due to weird quantum effects at the very edge of the event horizon, they slowly evaporate, emitting a faint glow now called Hawking radiation. This radiation is purely thermal, like the heat from a stove. It carries no information about what fell in. So, if a black hole eventually evaporates completely, radiating away all its mass as this random heat, then the information about everything it ever consumed is irretrievably lost. The universe's permanent shredder has now burned the shredded documents. This conclusion was so unsettling that Hawking himself initially bet against it, convinced a solution must exist. The search for that solution led to an even stranger idea, the firewall paradox. If information must escape, perhaps it is encoded in the Hawking radiation, but for that to happen, the event horizon cannot be the smooth, empty space Einstein predicted. Instead, it would have to be a searing wall of high-energy particles, a literal firewall that would incinerate anything crossing it. This creates a new problem because general relativity insists that crossing the event horizon should be uneventful, a principle called the no-drama theorem. An astronaut falling in would notice nothing special at the horizon before being stretched apart by tidal forces, so we are left with three impossible options. Information is destroyed, violating quantum mechanics, a firewall exists violating general relativity, or our understanding of space, time, and information is profoundly incomplete. The leading candidate for a solution comes from the holographic principle, which suggests all the information about what fell into the black hole is not lost inside, but is instead smeared across its two-dimensional event horizon like a cosmic hologram and slowly leaked out in the radiation. It is as if a three-dimensional sculpture were perfectly encoded into the pixels of a flat painting. The information is preserved, but in a form so scrambled and complex it appears as random noise. This paradox is not just an abstract puzzle for theorists, it cuts to the heart of what reality is. Is the universe fundamentally deterministic, where information about the past always dictates the future, or can information truly vanish, making history unknowable? The black hole information paradox tells us that where our greatest theories meet at the edge of infinite darkness, they whisper contradictory secrets about the nature of existence itself. The paradox of information at the edge of a black hole confronts us with the limits of our theories, but a far older mystery is etched into the very atoms of the stars themselves. Our most precise cosmological story begins with a dramatic event called Big Bang nucleosynthesis. In the universe's first 20 minutes, the entire cosmos was a searing, dense soup of protons and neutrons. As it expanded and cooled, these particles began to fuse, creating the first atomic nuclei. This brief, fiery forge set the chemical composition for everything that would follow. The calculations for this process are a triumph of modern cosmology. The predicted amounts of hydrogen and helium, the two lightest and most abundant elements, match the quantities we observe in the oldest regions of space with stunning accuracy. It is a powerful confirmation that we understand the broad strokes of the universe's first moments, yet nestled within that success is a single, glaring anomaly. The theory also predicts how much of a specific isotope, lithium-7, should have been forged in that primordial fire. When astronomers point their telescopes at ancient stars in the halo of our galaxy, stars that formed from nearly pure Big Bang material, they measure the lithium abundance. The observed amount is only about 1/3 of what the models say it should be. This is the lithium problem. A factor of 3 might not sound catastrophic, but in the precise world of primordial cosmology, it is a screaming discrepancy. It means something is missing from our picture. Either our understanding of nuclear physics in those extreme first minutes is incomplete, or something happened later to destroy the lithium in these ancient stars. The first possibility takes us back to the particle physics of the infant cosmos. Could unknown particles, like certain types of dark matter, have been present and altered the nuclear reaction rates? Perhaps the density of the early universe was not perfectly uniform in a way that affected lithium production. The second possibility looks to the stars themselves. These ancient suns are like cosmic fossils, and we assume their surface composition reflects the pristine gas from which they formed. But what if processes inside these stars slowly dragged lithium down from their atmospheres into their hot interiors, where it was destroyed? Or what if their surfaces were somehow diluted by lithium-free material later in their lives? After decades of study, neither explanation has fully solved the puzzle. Improved nuclear data and more sophisticated models of stellar interiors have chipped away at the discrepancy, but it stubbornly remains. The lithium problem is a tiny crack in an otherwise solid edifice, a reminder that our origin story, for all its grandeur, might still have a missing page. It tells us that the universe's first nuclear furnace left behind a signature we have yet to fully decipher, a subtle clue that the simplest atoms hold secrets from the dawn of time. The ancient lithium in the oldest stars points to a flaw in our cosmic accounting, but that is only the beginning of a much larger inventory problem. Dark matter and dark energy may dominate the universe, but even the ordinary matter, the stuff of stars, planets, and us, is not all present and accounted for. Based on the precise measurements of the cosmic microwave background and the light from distant quasars, cosmologists have a very good idea of how much normal or baryonic matter the universe should contain. Yet when we tally up everything we can see, all the galaxies, stars, gas clouds, and dust, we come up short, significantly short, about half of all the ordinary matter in the universe is simply missing. This is the missing baryon problem, and it is a different kind of mystery. We are not searching for an exotic, unknown substance, but for the very atoms we are made of, hiding in plain sight. The leading theory is that this missing matter is not in the bright, dense galaxies, but in the vast, empty spaces between them. Picture the cosmic web, the grand architecture of the universe, with galaxies strung along immense filaments of dark matter like pearls on a string. Between these filaments are unimaginably huge voids. Scientists believe the missing baryons are there, in those filaments, in the form of an extremely diffuse, superheated gas. This is the warm-hot intergalactic medium, or the WIM. It is a ghostly plasma, so thin it contains only a few atoms per cubic meter, a vacuum far better than anything we can create on Earth, but spread across billions of light years, its total mass becomes staggering. Detecting this wispy, invisible fog is one of the greatest observational challenges in modern astronomy. It is too hot to glow in visible light and too diffuse to cast a clear shadow. We need to catch it in the act of doing something, and that something is absorbing and filtering the light from the most brilliant beacons in the cosmos, quasars. Imagine a quasar as a distant lighthouse, its powerful beam of light traveling across the universe for billions of years. If that light passes through a filament of the WIM, the hot gas will imprint a faint fingerprint on the beam, absorbing specific wavelengths of ultraviolet and soft X-ray light. By carefully analyzing the spectra of hundreds of quasars, astronomers have begun to find these telltale absorption lines, like finding the silhouette of a ghost by the light it blocks. It is painstaking, indirect detective work. Recent observations from X-ray telescopes like XMM Newton have provided some of the most compelling evidence, detecting the faint glow of oxygen atoms heated to millions of degrees within these cosmic filaments. Each detection is a small piece of the puzzle, suggesting the WIM is real and that it may indeed hold the key to balancing the universe's ledger, yet the full accounting remains incomplete. We have found hints and patches of this intergalactic plasma, but not yet enough to confidently say we have found all 50%. The search continues, a hunt for the universe's hidden backbone, the hot, thin blood of the cosmic web that flows in the darkness between the islands of light. This ledger of missing ordinary matter is a puzzle of cosmic accounting, but the books are even stranger when we look at the balance sheets of individual galaxies. The mystery of dark matter is not a uniform blanket. It is a tapestry with shocking, threadbare patches and others woven from almost nothing else. Take the ultra-diffuse galaxy Dragonfly 44 floating in the Coma cluster. Through a telescope, it is a ghost, a wispy smear of starlight so faint it was overlooked for decades. Yet when astronomers measured the motions of its few visible stars, they were stunned. Those stars were whipping around at tremendous speeds, indicating the galaxy possesses the gravitational pull of a Milky Way, but with only 1% of the stars. Dragonfly 44 is, by mass, 99.99% dark matter. It is a cosmic skeleton, a halo of invisible mass that somehow failed to assemble most of the luminous matter we expect. Then, at the opposite extreme, we have galaxies like NGC 1052 DF2. This ultra-diffuse galaxy presents the inverse puzzle. Its stars move slowly, lazily, their speeds exactly matching the gentle pull of the visible stars alone. According to its rotation curve, the graph that plots stellar speed against distance from the center, there is no need for any dark matter halo at all. The line is flat where it should rise, indicating no hidden mass. How can this be? Our standard model of cosmology says galaxies form within cradles of dark matter. It is the gravitational seed that draws in gas, which then forms stars. A galaxy without dark matter is like a tree with no roots. It should not exist, or at least it should not have formed in the way we understand. One compelling theory is that these oddballs are the products of galactic violence. Perhaps a dark matter-free galaxy is a remnant, a pocket of stars and gas that was violently stripped from a larger galaxy during a past collision, leaving its dark matter halo behind. It is a cosmic orphan, a fragment sailing on without its invisible parent. The dark matter-dominated ghosts like Dragonfly 44 might be failed galaxies, places where the dark matter cradle was present, but for some reason the process of gas accumulation and star formation was incredibly inefficient, leaving a vast reservoir of darkness with only a sprinkling of stars. These outliers are not mere curiosities, they are critical stress tests for our theories. If dark matter is a particle that interacts only through gravity, then it should be possible to separate it from normal matter in a violent encounter. Finding galaxies that appear to have done just that is tantalizing evidence for that particle nature. Conversely, if some alternative theory of gravity is correct, modifying the laws to explain rotation curves without dark matter, then it must also explain why these same modified laws do not seem to apply in places like NGC 1052 DF2. The rotation curve is the key signature. For a typical spiral galaxy, we expect stars closer to the center to orbit quickly, and those farther out to slow down, just as planets in our solar system do. Instead, the curves are flat, stars far from the luminous center orbit just as fast as those near-in, a clear sign of unseen mass holding them tight. Placing the rotation curve of a Milky Way-type galaxy next to that of a dark matter-free galaxy is like comparing a deep, resonant hum to a shallow whisper. One speaks of a hidden presence, the other of a puzzling absence. By studying these extremes, astronomers are not just hunting for what dark matter is, but also for what it is not and how it shapes or fails to shape the visible universe. Each bizarre galaxy is a natural experiment, a clue written in the slow dance of stars, telling us that the story of dark matter is far more complex and strange than a simple, universal ingredient. These contradictory galaxies force us to question the very scaffolding of the cosmos, but there is a more fundamental number that refuses to be pinned down. The universe's expansion rate, called the Hubble constant, is one of the most critical parameters in all of cosmology. It tells us not only how fast space is stretching, but also the age of the universe and its ultimate fate. For decades, astronomers have worked to measure this number with ever greater precision. The shocking result is that we now have two extremely precise, yet stubbornly different answers. This discrepancy is the Hubble tension, and it is not a small margin of error. It is a glaring crack in the foundation of our understanding. One method looks back to the dawn of time. By studying the detailed patterns in the cosmic microwave background, the afterglow of the Big Bang, scientists can calculate what the expansion rate should have been in the infant universe and, using our standard model of cosmology, predict what it should be today. This is like finding a baby picture with a precise height marked on it and using a known growth chart to predict the adult's height. The result from this cosmic baby picture is an expansion rate of about 67 kilometers per second per megaparsec. The other method measures the universe directly in its current state. Astronomers use a cosmic distance ladder, a meticulous chain of measurements starting with nearby stars called Cepheid variables, whose predictable pulsations reveal their true brightness, and extending out to distant supernovae which act as standard candles. This is like measuring the current height of the adult directly. This local measurement consistently gives a faster expansion rate, around 73 kilometers per second per megaparsec. The difference is only a few units, but in the realm of high-precision cosmology, it is a massive and persistent gap. These are not rough estimates. Each method has been refined over years, with teams cross-checking their data and minimizing uncertainties. The error bars, those little lines on a chart representing the range of possible values, no longer overlap. The two most trusted ways of measuring the universe's most important speed are telling us two different stories. Imagine two of the world's most accurate clocks, both impeccably engineered, one consistently ticking just a fraction faster than the other. That tiny difference points to a fundamental flaw in the mechanism. The Hubble tension suggests something is missing from our standard model of cosmology, the lambda-cold dark matter model. Perhaps dark energy is not constant but has evolved over time, growing stronger or weaker in a way we have not accounted for. Maybe dark matter interacts with itself or with normal matter in subtle ways we have not detected. There could be unknown types of neutrinos, or perhaps the universe is slightly lopsided on a grand scale, affecting our measurements. Some have even speculated about the influence of a primordial magnetic field from the universe's first moments. Each proposed fix is a potential revolution in physics, a clue that our map of cosmic history needs a serious revision. This tension is more than a technical disagreement, it is a beacon. It tells us that the universe is hiding one more secret about its own engine, and that by chasing this discrepancy between its ancient light and its modern expansion, we might be on the verge of discovering an entirely new chapter in the laws of physics. The Hubble tension is a crack in our cosmic model, a sign that something fundamental is missing from the equations. But what if the missing ingredient is not just a new property of dark energy or dark matter, but an entirely new form of reality? This brings us to one of the most speculative and mind-bending ideas in modern physics, the concept of the unparticle. Forget protons, neutrons, or even the hypothesized particles of dark matter. The unparticle is something else entirely. It proposes a hidden sector of the universe, a shadow realm composed of stuff that does not behave like particles at all. In our everyday world and in the standard model of particle physics, everything is quantized. Energy comes in discrete packets, matter is made of indivisible particles, and forces are carried by specific messengers like photons. The unparticle challenges this at its core. It is scale invariant. This means it has no characteristic mass or size, no defining scale that makes it act one way at high energies and another way at low energies. A true unparticle field looks the same no matter how close you zoom in or how far you zoom out, like a perfect fractal pattern that repeats infinitely. Because of this, it would not manifest as distinct particles with specific properties you can count. You could not point to an unparticle and say it has this much mass or that much spin. Instead, it would behave as a continuous, fluid-like substance with fractional properties, blurring the line between a particle and a wave in a way we have never seen. How could such a bizarre thing exist? The theory, first proposed by physicist Howard Georgi, suggests that at extremely high energies, far beyond what our particle colliders can reach, there could be a hidden sector of particles that interact with our own familiar matter only through gravity or incredibly weak forces. As the universe cooled, these hidden particles could undergo a phase transition, losing their particle-like nature and condensing into this scale-invariant unparticle stuff. If it exists, it would be everywhere, a pervasive, ghostly medium woven into the fabric of space itself. The implications are staggering. This continuous, ethereal substance could be a candidate for dark matter itself. Its gravitational influence would be felt, but because it does not clump into neat particles, it might explain why dark matter halos around galaxies have certain smooth, diffuse profiles that some particle models struggle with. It could also mediate new, incredibly feeble forces between ordinary matter, forces so weak they have escaped all detection so far, but which might subtly influence the expansion of the universe or the behavior of neutrinos. Testing for the unparticle is a monumental challenge. You cannot build a detector to catch one because they are not ones. Instead, physicists look for its subtle signatures in the most precise experiments we have. They search for tiny deviations in the way particles scatter off each other in colliders, for minute distortions in the gravitational pull between carefully controlled masses, or for anomalous energy losses in certain nuclear reactions. It is like trying to prove the existence of fog by measuring the faintest possible dimming of a distant street lamp. So far, there is no evidence. the unparticle remains a beautiful mathematical possibility, a testament to the human imagination's ability to conceive of realities beyond our senses. It forces us to ask a profound question. Is our universe ultimately particulate, built from tiny, discrete Lego blocks, or could its deepest foundations be something far more fluid and strange, a continuum where the very idea of a particle dissolves into a seamless, scale-less whole? If the universe's foundations might be a seamless continuum, then the structures it builds should be random and without direction. Yet, when we map the most violent engines in the cosmos, a pattern emerges that feels anything but random. Across billions of light-years, the colossal jets erupting from quasars, the supermassive black holes feasting at the hearts of ancient galaxies, appear to be pointing in the same direction. It is as if countless cosmic lighthouses scattered across an ocean of time and space have somehow agreed to shine their beams along a shared axis. This is the mystery of quasar alignment. Quasars are not uniform. Their powerful jets shoot out along the rotational axis of the swirling, superheated disk of material falling into the black hole. That axis can point anywhere. In a universe governed by chance, the jets of quasars separated by distances so vast that light has taken billions of years to travel between them should be oriented randomly, like pins dropped from a great height. But detailed studies of hundreds of quasars using radio telescopes to map their jet directions have revealed a shocking correlation. Over scales approaching 4 billion light-years, their rotational axes show a significant degree of alignment, as if they are all spinning in concert with some invisible cosmic current. This is not a small local effect, it is a coordination across nearly a third of the observable universe. The force required to orchestrate such alignment is unimaginable. It suggests the influence of something primordial, a fossil imprint from the universe's first moments. One leading theory points to cosmic inflation, that period of faster-than-light expansion in the first fraction of a second after the Big Bang. Inflation could have stretched quantum fluctuations in a primordial field into vast, coherent patterns that later seeded not only the distribution of matter, but also the preferred spin directions of the largest structures. It is like blowing up a balloon with tiny, random wrinkles, only to find that when it is fully inflated, all the wrinkles line up along the same seam. This alignment whispers of a universe born with a subtle grain, a texture woven into the fabric of space-time that still guides the spin of monsters billions of years later. But if aligned quasars hint at a cosmic grain, then their gatherings threaten to tear the fabric of our cosmological principles entirely. We call these gatherings large quasar groups, and their scale is almost incomprehensible. The huge Large Quasar Group, discovered in 2013, is a structure over 4 billion light-years in its longest dimension. To grasp that, consider our entire local supercluster, Laniakea, is a mere 500 million light-years across. This group of quasars is 8 times larger. It contains 73 quasars, each one a beacon from a young galaxy with a voracious black hole at its core, all bound together in a structure that should not exist. According to the cosmological principle, a cornerstone of modern cosmology, the universe should look roughly the same in every direction when viewed on sufficiently large scales. Matter should be evenly distributed. There is a theoretical size limit, about 1.2 billion light-years, beyond which such immense structures should not form. The huge Large Quasar Group smashes through that limit with ease. It is not just an outlier, it is a challenge written in fire across the sky. Finding such a structure is like studying a vast forest and believing the trees are randomly scattered, only to step back and see they have formed a perfect continent-spanning arrow. Its existence forces a difficult choice. Is the cosmological principle simply wrong, or at least only an approximation? Could the universe be lumpy and structured on scales far grander than we ever anticipated? Or does this immense group point to something even stranger, like a defect in the early universe's expansion, a place where inflation ended differently, leaving behind a titanic scar of concentrated matter? These aligned beacons and their impossible gatherings tell a story of a cosmos that is not just expanding, but one that may have been imprinted with architecture and alignment from its very first breath. They suggest that the seeds of order planted in the fiery dawn grew into patterns so vast we are only just beginning to trace their outlines against the dark. The alignment of quasars across billions of light years hints at a universe with a deep and subtle grain, but the oldest light of all reveals a feature that feels less like texture and more like a bruise. This is the cold spot, one of the most enduring anomalies in the cosmic microwave background. In the finely detailed map of the infant universe's afterglow, it stands out as a circular region significantly colder than the surrounding average, a vast chill in the primordial sky roughly 1.8 billion light-years across. It is not the only irregularity, but its size and statistical significance make it a profound outlier, a place where the universe's first whisper came out a fraction of a degree quieter. For years, astronomers sought a culprit within the universe we know, and they believed they may have found one. Lying in the same direction, about 3 billion light-years away, is the Eridanus supervoid. A void is not a true emptiness, but a region of space where the density of galaxies is far lower than average, a cosmic desert on a gargantuan scale. The Eridanus supervoid is one of the largest structures ever identified, a spherical emptiness spanning an incredible 1 billion light-years. The leading theory to connect them is a subtle but powerful effect called the integrated Sachs-Wolfe effect. As light from the cosmic microwave background travels across the expanding universe, it climbs in and out of gravitational wells created by clusters of matter and valleys created by voids. If the universe's expansion is accelerating due to dark energy, as we know it is, these wells and valleys evolve as the light passes through. This can impart a small energy change to the photons. When light crosses a vast, deep void like the Eridanus supervoid, it loses a tiny bit of energy climbing out of the gravitational valley, which manifests as a slight cooling or reddening of that light in our maps. It is a cosmic toll paid on a journey through nothingness. The problem is one of scale. The observed cold spot is too big and too cold. Detailed calculations suggest the Eridanus supervoid, while immense, is likely not substantial enough, or perhaps not empty enough, to produce the full magnitude of the cooling we see through this effect alone. The numbers do not quite add up, leaving a gap in the explanation. This mismatch has fueled a more spectacular hypothesis. Could the cold spot be a collision scar, a bruise left on our universe from a primordial impact with another bubble universe in the multiverse? In this mind-bending scenario, the collision would have drained energy from that region of space in the earliest moments, imprinting a permanent cold patch on the cosmic microwave background. It is a theory that stretches from the bedrock of cosmology to the frontiers of speculation. The debate remains active and unresolved. Some researchers argue that the supervoid and the cold spot are a chance alignment, two rare but separate features that happen to lie along the same line of sight. Others are investigating whether a chain of smaller, interconnected voids could amplify the effect. The maps tell a compelling visual story, placing the circular chill of the cold spot over simulations of the vast, empty bubble of the Eridanus supervoid, a ghostly imprint overlapping a cosmic blank. Whether it is a signpost to a multiverse or simply a reminder of how poorly we understand the largest structures in our own, the cold spot stands as a persistent, quiet anomaly in the universe's first light, a place where the expected warmth of creation is missing, leaving behind a chill we have yet to fully explain. The primordial chill of the cold spot speaks of a quiet, ancient anomaly, but some cosmic objects announce their presence with a violence that can be felt across the galaxy. Among the densest, most magnetic objects in existence, a neutron star known as a magneta reigns supreme. Picture the collapsed core of a giant star, a city-sized sphere of pure neutron matter so dense a single teaspoon would weigh 1 billion tons. Now amplify its magnetic field to a level 1,000 trillion times stronger than Earth's. This is a magnetar, a cosmic powerhouse where the very rules of physics are bent by unimaginable force. Its magnetic field is so intense it can twist the star's rigid iron crust, creating starquakes, seismic events on a stellar scale. When the crust finally snaps, it unleashes a cataclysm. For a fraction of a second, the magnetar can outshine every star in the Milky Way combined, releasing more energy than our Sun will emit in 100,000 years. We see this as a giant flare, a sudden, blinding spike of X-rays and gamma rays, but the magnetar's fury is not always a single, catastrophic rupture. Some of these objects, dubbed soft gamma repeaters, fire off repeated, less intense salvos. They are cosmic repeat offenders, sending bursts of softer gamma radiation across the galaxy in unpredictable patterns, like a temperamental lighthouse flashing without a schedule. The mechanism is a violent dance of magnetic reconnection, where the star's impossibly twisted magnetic field lines suddenly snap and reorganize themselves, converting colossal magnetic energy into radiation and particle acceleration in an instant. The power is so great that in 2004, a magnetar flare from 50,000 light-years away from a star named SGR 1806-20 actually affected our planet. For a brief moment, it ionized Earth's upper atmosphere, disrupting long-range radio communications and significantly compressing our magnetosphere on the side facing the burst. A starquake on a city-sized object halfway across the galaxy reached out and touched our world. Understanding these events is a frontier of extreme physics. Scientists use sophisticated models to simulate the cracking of the neutron star crust and the subsequent release of energy, visualizing it as a network of fractures spreading across the surface, each one unleashing a torrent of radiation. The light curves from these events, the graphs of their brightness over time, tell a story of sudden ignition and rapid decay, a signature as unique as a fingerprint. Yet the precise trigger for the final, catastrophic snap, and how exactly the magnetic energy is converted so efficiently into gamma rays, remains an active puzzle. Are there specific fault lines in the crust? Does the superfluid core of the neutron star play a role in driving the instability? Each giant flare is a natural laboratory, testing our theories of matter under conditions so extreme they can never be recreated on Earth. These magnetic monsters remind us that the universe is not only vast and ancient, but also capable of concentrated, furious violence on a scale that defies human intuition. A reminder written in bursts of light that cross galactic distances to whisper of forces beyond our comprehension. These magnetic monsters unleash forces that can be felt across the galaxy, but to measure them or anything else, we rely on the precise trajectories of our robotic explorers. For decades, a faint but persistent whisper in the data from these spacecraft has defied explanation. When engineers send a probe on a grand tour of the solar system, they often use a gravity assist, a celestial slingshot that uses a planet's gravity to fling the spacecraft onward, saving precious fuel. The math for these maneuvers is a masterpiece of celestial mechanics, predicting the probe's speed down to the millimeter per second. Yet, on multiple occasions, something has gone subtly wrong. As spacecraft like Galileo, Near, and Rosetta swung past Earth, they experienced a tiny, unexpected change in velocity. This is the flyby anomaly. The effect is minuscule, a shift of a few millimeters per second, but in the pristine, predictable environment of interplanetary space, such a discrepancy is a glaring red flag. It is as if the universe were adding a faint, unseen nudge to our machines as they whip around our planet. Imagine plotting the spacecraft's expected path as a smooth, perfect arc on a graph. The flyby anomaly shows up as the actual data points drifting just a hair away from that line, a consistent error that appears only during the Earth's close approach and then vanishes. Teams of scientists have chased every conceivable cause. Could it be the drag from Earth's tenuous outer atmosphere? Detailed models say no, the effect is too high. What about the pressure of radiation from the sun, or even heat radiating from the spacecraft itself, like the Pioneer anomaly? Meticulous accounting has ruled these out. Some have proposed more exotic ideas, like subtle flaws in our understanding of Earth's gravity field, or even minute effects from the planet's rotation dragging on space-time itself, a phenomenon called frame dragging. But the numbers never quite add up. The flyby anomaly remains an unsolved whisper in the navigational data, a reminder that even in our own celestial backyard, the laws of physics might have a footnote we have yet to read. If the flyby anomaly is a whisper in the motion of machines, then the next mystery is a deafening roar in the silent channels of the cosmos. When astronomers first pointed radio telescopes at the sky, they expected to hear the faint hiss of ancient events, the combined radio whispers of distant galaxies, and the afterglow of the Big Bang. Instead, they discovered the sky was shouting. This is the space roar, an unexpectedly loud blast of static that blankets the entire sky at low radio frequencies. It is not a signal from a single point, but a diffuse, all-pervasive background noise about 6 times louder than anyone predicted. Think of tuning an old analog radio between stations, expecting to hear a soft, uniform static, the sound of the universe's ambient temperature. The space roar is like turning the volume on that static up to an ear-splitting level with no dial to turn it down. Its source is a complete enigma. We know what it is not. It is not the combined radio emission from all the known galaxies in the universe. That sum is far too quiet. It is not the cosmic microwave background, which peaks at much higher frequencies. Could it be the collective murmur from vast oceans of hydrogen gas in the early universe, glowing with a radio hum we have misjudged? Or is it the signature of countless faint radio galaxies, their emissions blurred into a uniform fog? The problem is, even when we add up every conceivable known source, the roar drowns out the calculations. Some have wondered if it could be a local effect, perhaps emissions from our own Milky Way that we do not fully understand, or even an unknown artifact in the instruments themselves. But the roar has been detected by multiple independent experiments, including the Arcade instrument flown on a high-altitude balloon, which confirmed its staggering intensity. Maps of this radio sky show not points or structures, but a uniform, fiery glow, a cosmic canvas painted in a color of noise we cannot explain. It is the soundtrack of the universe turned up to 11, and we have no idea who or what is controlling the volume. This pervasive static is a fundamental background against which all other radio astronomy must be conducted. A reminder that for all our listening, the cosmos may be filled with a conversation in a language we have not yet learned to hear. That deafening radio roar is a reminder of how much we still have to learn about the universe's most basic components, and sometimes the deepest mysteries are hidden within the smallest things. The final frontier of the unknown is not always in deep space, but inside the atom itself. Our last 2 cosmic phenomena take us from the vastness of the cosmos to the heart of matter, where fleeting particles and mismeasured sizes threaten to rewrite the rules of everything. We begin with a ghost that should not exist, the tetraneutron. In the core of every atom except hydrogen, protons and neutrons are bound together by the strong nuclear force, one of the universe's fundamental interactions. The rules governing this force are clear. Neutrons are social particles, but they need protons to form stable nuclei. According to every reliable model of nuclear physics, a cluster of only neutrons with no protons to mediate the binding should fly apart instantly. It is like trying to build a stable arch using only identical repelling magnets. The structure should collapse in a fraction of a second. Yet, in particle accelerator experiments, where scientists slam atomic nuclei into targets at incredible speeds, hints of something impossible have appeared. On at least 2 separate occasions, researchers have detected signatures consistent with a particle made of 4 neutrons, a tetraneutron, surviving for a mere 10 to the power of negative 22 seconds before decaying. That timescale is so brief it is essentially an instant, but in the world of particle physics, it is just long enough to suggest a resonance, a fleeting, temporary state of matter. The implications of a confirmed tetraneutron are staggering. It would mean our understanding of the strong force is incomplete, that neutrons can bind in ways our theories do not allow. This would not just be a new particle, it would be a crack in the foundation of nuclear physics, forcing us to reconsider the glue that holds all atomic nuclei together. The entire periodic table and the stability of all matter rests on this force. Finding a stable or even quasi-stable tetraneutron would be like discovering a new law of architectural physics that allows magnets to stick together in a way we thought was forbidden, reshaping our understanding of every structure built from them. If the tetraneutron challenges how particles bind, then the proton radius puzzle calls into question the size of a particle we thought we knew intimately. The proton is not a tiny, solid billiard ball. It is a fuzzy cloud of quarks and gluons, and physicists have worked for decades to measure its charge radius, the effective span of its influence. For years, 2 highly precise methods agreed. You could measure it by bouncing electrons off protons in scattering experiments, or you could study the energy levels of hydrogen, the simplest atom, which are exquisitely sensitive to the proton size. These methods converged on a comfortable value. Then, around 2010, a team tried a different approach. They created not ordinary hydrogen, but muonic hydrogen, where the electron is replaced by its heavier, unstable cousin, the muon. Because the muon orbits 200 times closer to the proton, it is far more sensitive to the proton size. The measurement they obtained was shockingly different. The proton's radius came out 4% smaller than the established value. 4% may seem trivial, but in the world of precision quantum physics, it is a chasm. It is the difference between measuring the width of a hair and finding it is suddenly, definitively, a different width when you use a different, even more precise microscope. This is not a margin of error, it is a direct conflict. Either the experiments with ordinary hydrogen have a hidden, systematic flaw we have missed for 50 years, or something is fundamentally wrong with our theory of quantum electrodynamics, the stunningly successful theory that describes how light and matter interact. This theory underpins everything from chemistry to the stability of atoms. The discrepancy has spurred a global effort with new experiments using both electronic and muonic hydrogen, as well as other exotic atoms. Some recent results have edged closer to agreement, but the puzzle is not fully resolved. It whispers that our map of the subatomic world, the very bedrock of material reality, might have a tiny, crucial landmark in the wrong place. Together, the tetraneutron and the proton radius puzzle represent a profound truth. The greatest cosmic mysteries are not always found in the voids between galaxies or in the afterglow of creation. They can be locked within the nucleus of a single atom, in the fleeting existence of a particle that should not be, or in the stubborn disagreement over the size of a fundamental building block. Solving these puzzles would not just add new facts to a textbook, it would mean revising the blueprint of reality itself, the instructions from which every star, planet, and person is built. The universe's final secrets may be written in the smallest of scripts. That blueprint of reality, with its questionable proton size and forbidden particles, leads us to a final, overarching question that ties every prior mystery into one breathtaking and perhaps unsettling possibility. Why does this particular universe exist at all, and why are its rules so perfectly arranged for us to be here asking the question? This is the mystery of fine-tuning. The fundamental constants of nature, like the strength of gravity, the mass of an electron, or the energy in empty space we call dark energy, are not predicted by any theory. They are numbers we must measure and plug into our equations. Change any one of these values by even a minuscule amount, and the universe as we know it vanishes. If the strong nuclear force were just a few percent stronger, all hydrogen would have fused into helium in the Big Bang, leaving no fuel for stars. A few percent weaker, and no complex atomic nuclei could form at all, preventing the existence of carbon, oxygen, and life. If dark energy were slightly more potent, the universe would have expanded so rapidly that galaxies and stars never had a chance to coalesce. Slightly weaker, and it would have collapsed back on itself long before life could arise. The list goes on, creating a razor's edge of viability. It feels as though a cosmic designer dialed in dozens of independent, arbitrary numbers with impossible precision to allow for planets, chemistry, and ultimately conscious observers. This apparent fine-tuning is so striking that it demands an explanation. One answer is the anthropic principle, a simple but profound logical statement. The universe must be compatible with the existence of observers because we are here to observe it. In an infinite variety of universes with different laws, we would, of course, find ourselves only in one that allows our existence. It is a tautology, but it shifts the perspective from why is our universe special to we could only ever find ourselves in a universe that allows us. This thinking naturally leads to the multiverse hypothesis, the grandest speculative framework in all of science. The idea is that our Big Bang was not a unique creation event, but one bubble in an eternally inflating cosmic foam. Picture an infinite, bubbling cauldron of space-time, where new universes constantly nucleate, each with its own random set of physical laws and constants. Most of these bubble universes would be stillborn or barren, collapsing instantly or expanding into empty, structureless voids. But in a near-infinite ensemble, a tiny fraction will, by pure chance, have the exact right combination of numbers to produce stars, galaxies, and life. We are not in a fine-tuned universe. We are in one of the inevitable, albeit rare, universes that is tuned just right. The multiverse offers a potential explanation for many of our deepest puzzles. The inexplicable value of dark energy. In most universes it is too high or too low, but we find ourselves in one where it allows for galaxy formation. The strange initial conditions seen in the cosmic microwave background, they are simply the local geography of our particular bubble. Even the bizarre hypotheticals like the unparticle or cosmic strings could be realities in other bubbles with entirely different physics. This idea finds some support in the leading theory of the universe's first moments, cosmic inflation. The mathematics of inflation suggest it may be eternal, inevitably producing a fractal landscape of disconnected universes. Yet the multiverse remains, by its very nature, almost impossible to test. If these other universes are causally disconnected from our own, forever beyond our cosmic horizon, can their existence ever be more than a philosophical proposition? Some scientists propose looking for scars on our own universe, like the cold spot in the cosmic microwave background, as potential evidence of a primordial collision with another bubble. Others search for subtle statistical fingerprints in the distribution of galaxies, but for now, it stands as the ultimate speculative answer, a framework that exchanges the mystery of fine-tuning for the vast, perhaps untestable, mystery of an infinite ensemble of realities. It ties together the proton's puzzle and the galaxy's rotation, the lithium problem and the Hubble tension, into a single, staggering narrative. We are left gazing at the stars not as the only show in existence, but as a single, glowing window in an infinite mansion of darkness, each room governed by different, unthinkable laws. The final cosmic phenomenon we do not understand may not be a single object or force, but the very nature of reality's portfolio and our unimaginably lucky place within it. But that infinite mansion of darkness is not a prison for our curiosity. For every profound question the cosmos has posed, humanity is already forging new keys. This is not an era of passive wonder, but of active, revolutionary investigation. The next generation of tools now being built or launched will peer deeper, listen more closely, and smash matter together with greater force than ever before, each one designed to crack open a specific cosmic mystery. The journey from bewildering question to groundbreaking answer is accelerating. Already, the James Webb Space Telescope is rewriting the first chapters of cosmic history. Positioned 1,000,000 miles from Earth, its infrared gaze cuts through cosmic dust to see the formation of the very first galaxies, those faint sparks igniting after the Big Bang's long dark age. By analyzing the atmospheres of distant exoplanets, it can search for the chemical signatures of life, turning the tantalizing whispers of Martian methane into a chorus of data from worlds orbiting other stars. It is our time machine to the dawn of structure. On a Chilean mountaintop, the Vera C. Rubin Observatory is preparing for a different kind of revelation. With a camera the size of a small car, it will not stare at one patch of sky, but scan the entire visible heavens every few nights for a decade. This relentless survey will create a cosmic motion picture, revealing anything that changes or moves. It will find millions of new asteroids and icy objects at the solar system's edge, potentially pinpointing the source of the Kuiper Belt Cliff or discovering the hypothetical planet 9. It will map the subtle distortions of dark matter across the sky in unprecedented detail and catch the fleeting flash of countless supernovae, refining our measurement of dark energy and perhaps resolving the Hubble tension once and for all. While these telescopes watch the light, another revolutionary observatory will listen for the ripples in space-time itself. The Laser Interferometer Space Antenna, or LISA, will be a fleet of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. This exquisite instrument will detect gravitational waves at frequencies impossible to sense on Earth, opening a completely new window on the universe. It will hear the mergers of supermassive black holes from the epoch of galaxy formation, probe the structure of spacetime around black holes, and potentially detect cosmic strings or other exotic relics from the Big Bang. It is a stethoscope for the fabric of reality, and back on Earth, the quest continues in tunnels deep underground and in colossal rings of steel. Next-generation particle colliders, like the proposed Future Circular Collider, aim to reach energies far beyond today's machines. They will hunt for the hypothetical particles that make up dark matter, probe the conditions of the early universe microseconds after the Big Bang, and search for any hint of extra dimensions or new symmetries in nature. They are our microscopes turned up to cosmic power, seeking the answers to the proton radius puzzle and the nature of the strong force in the debris of controlled, violent collisions. Each of these tools is a promise. The James Webb Space Telescope promises to show us our origins. The Vera C. Rubin Observatory promises a complete inventory of our changing sky. LISA promises to let us hear the universe's hidden symphony, and new colliders promise to reveal the underlying rules of everything. Together, they represent a coordinated assault on ignorance, a global scientific endeavor to pull back the curtain on dark matter, to measure the true nature of dark energy, to find the missing baryons, and to listen for the echoes of the first moments. The mysteries we have explored are not dead ends, they are maps, and we are now building the vehicles to travel them. The greatest discoveries in the history of our species likely lie not in our past, but in the data streams of these magnificent machines, waiting to transform our whispers of wonder into a confident, collective understanding of our spectacular and strange home. These grand telescopes and silent detectors are not just machines of glass and steel, they are extensions of our deepest human impulse to look up and ask why. The drive to solve these cosmic puzzles does more than satisfy curiosity, it reshapes our world. Every mystery on this list has been a silent engine of progress, pushing the boundaries of technology in ways that ripple back into our daily lives. The need to see fainter objects forced the invention of charge-coupled devices, the very same CCD sensors that now live in every smartphone camera. The quest to detect gravitational waves demanded laser stabilization techniques of impossible precision, advancing fields from medical imaging to quantum computing. To listen for the faint radio whispers of the cosmos, we had to invent new ways to process vast oceans of data, birthing algorithms that now help diagnose diseases and predict weather patterns. The cosmic frontier, in seeking to answer the biggest questions, consistently delivers the tools to improve the smallest details of human life. This quest is also a powerful unifier, a rare endeavor where competition gives way to collaboration on a planetary scale. The Event Horizon telescope that captured the first image of a black hole was not a single instrument, but a synchronized array of observatories spanning from the high deserts of Chile to the volcanoes of Hawaii and the frozen plains of the South Pole. It required scientists from dozens of nations and cultures to align their schedules, share their data, and combine their expertise, all focused on a single, shadowy goal. The International Space Station, a city in the sky, is a testament to what humanity can build when we look outward together. These mysteries dissolve borders, creating a shared mission that transcends politics and reminds us of a common identity as explorers of a vast and puzzling home. Perhaps most importantly, these unanswered questions are the spark for the next generation. A child gazing at an image from the James Webb Space Telescope, at those swirling nascent galaxies or the haunting pillars of creation, is not just seeing pretty pictures. They are being handed a direct invitation to a story that is still being written. They are seeing that the universe is not a solved puzzle in a textbook, but a living, breathing mystery with blank spaces waiting for their names. Every young mind that wonders about the nature of dark matter or the fate of a wandering interstellar object is a potential physicist, engineer, or programmer whose future work might unlock solutions we cannot yet conceive. These cosmic enigmas are the ultimate curriculum, teaching not just facts but humility, patience, and the relentless power of a question. And that leads us to the deepest impact of all, the philosophical shift that comes from staring into the unknown. To confront the Fermi paradox is to grapple with our solitude and our responsibility. To understand the Hubble tension is to accept that our most cherished maps of reality may be incomplete. This journey does not diminish us, it ennobles our place within the grand narrative. We are not passive residents of a finished cosmos, we are its conscious participants, the universe itself developing a way to understand its own origins and fate. The realization that over 95% of reality is unknown is not a testament to our ignorance but to our potential. It means the story is still in its early chapters and we hold the pen. The true value of these 30 mysteries, from the galactic to the subatomic, is not merely in the answers we may one day find. It is in the act of searching itself, a perpetual reminder that to be human is to reach into the darkness, not out of fear, but with the unwavering belief that there is light to be found. So the stage is set and the questions hang in the air like constellations. We have wandered through shadows and light, from the impossible geometry of Saturn's storm to the silent, screaming mathematics of the proton. Now this journey turns to you. Look back at the gallery of cosmic oddities we have explored. Which one captures your imagination and refuses to let go? Is it the fleeting, brilliant scream of a fast radio burst, a millisecond of power from an unknown engine? Does your mind return to that silent, tumbling visitor, Oumuamua, and its strange acceleration as it departed our solar system, a cosmic postcard we barely had time to read? Or does the grandest puzzle call to you, the invisible presence of dark matter, the ghostly scaffolding holding every galaxy together that we can feel but cannot see? Perhaps it is the haunting silence of the Fermi paradox that lingers, the profound quiet where we expected a chorus. Each mystery is a door, and behind it lies not just an answer, but a potential revolution in our understanding of reality. This is where the conversation truly begins. I want to hear your theories, your wildest, most speculative ideas. Do you think fast radio bursts are the exhaust trails of alien starships or the death cries of collapsing dimensions? Could Oumuamua have been a fragment of an ancient, shattered world from another star, or something far more intentional? Is dark matter a sea of particles from a parallel universe bleeding into our own? There are no wrong answers here, only the spark of curiosity. Drop your thoughts in the comments below. Tell me which mystery keeps you up at night and why. Let us build a community of cosmic detectives, piecing together the puzzle from every angle. Your perspective might be the very one that connects a dot no one else has seen. The universe's greatest secrets are waiting, and the next clue could come from anywhere, even from you. From the shimmering hexagon on Saturn to the ghostly pull of a missing planet, from a single, screaming proton to the silent, accelerating void, these 30 enigmas are not failures of science. They are its fuel. Each one, from the impossibly small radius of a proton to the unfathomably vast stretch of dark energy, marks a frontier. They are the blank spaces on our map of reality, the questions that keep our telescopes pointed upward and our minds racing through the night. To stand before such mysteries is not a position of weakness but of incredible potential. It means the story is not over, the universe is still speaking, and we are learning how to listen. So the next time you find yourself under a clear night sky, remember this: you are not just looking at points of light. You are gazing at a grand, interconnected puzzle, a cosmic conversation between gravity and light, between the known and the unimaginable. Every star is a question, every dark patch a promise of something yet to be understood. Stay curious, keep looking up, and if you want to join us as we chase the next great unknown, be sure to subscribe. The universe has only begun to share its secrets.